Hello guys, so in this video we're going to go over a concept of spherical coordinate integrals. So basically, if you've already done cylindrical, it's different. Notice how we have a lot more conversion factors here. We have all the ones for cylindrical coordinates, plus we have x, y, z goes to r theta z goes to rho theta phi. And notice how we have our dv changes, so it's rho squared. Note that's not a p, that's rho. Sine phi, dp, d theta, d phi. And then we have our conversions. X is equal to r cosine theta, y is equal to r sine theta. And now here's these new conversions. R is equal to rho times sine theta. Therefore, x is equal to rho sine theta, r cosine theta, rho sine theta, cosine, rho sine phi cosine theta. Y is equal to rho sine phi sine theta. Z is equal to sine phi. So now what we're going to do is we're going to draw out what this looks like. So it's a region with the perfect sphere of radius 2 centered at the origin. So this is our positive z, positive y, and positive x axis, and our sphere looks something like this. So basically, the radius is 2, and this is a perfect sphere. So this is ideal when doing cylindrical coordinates. So for step 1, we're going to identify f of x, y, z, and dv. And quick note, do not confuse theta with phi, because they are two different things, and that's a common mistake with cylindrical coordinates. So note that theta and phi are two different things. So make sure you don't confuse them or use them interchangeably, because they're not interchangeable. So now f of x, y, z is given to us as, in the problem statement, 4x squared plus y squared plus z squared raised to the 4th power. And our dv is also given to us in the conversions, so it's rho squared times sine phi d rho d theta d phi. So now let's move on. So note the conversion factor from xyz to spherical coordinates is rho theta phi. So for step 2, we're going to convert to spherical coordinates. So note the function given to us of f of x, y, z was 4x x squared plus y squared plus z squared to the 4th power. And note another conversion factor, x squared plus y squared plus z squared is equal to rho squared. So what we can do with this is we can substitute rho squared and raise it to the 4th power. And when we simplify the exponent, it's 4 times rho to the 8th power. So that's our spherical coordinate. That's our f of x, y, z. But instead now it's f of rho theta phi times dv. So rho theta phi times rho squared sine phi. This is our dv. And then d phi, or d rho, d theta, d phi. So now, let's find the bounds of integration. Well, since this is an ideal perfect sphere, this one's very straightforward. So our rho initially starts at 0 because it's centered at the origin, and the outer bound is 2. Why? Because it's a radius of 2. So therefore our bounds for rho are from 0 to 2. And the problem told us it was a perfect ball sphere centered at the origin with the radius of 2. So what about theta? So theta goes from 0 to 2 pi. And this is always the case unless otherwise specified, because it's a full sphere, and the full sphere on the xy plane is from 0 to 2 pi. If you think about just a circle, it's from 0 to 2 pi. And now our rho, our phi, is 0, but the upper limit is actually just pi. It's not 2 pi. Why? Because this is always the case. But why is that? Why is it not 2 pi and why is it pi? Well, that's because phi, the sphere, when we take into account the phi axis, it only revolves 180 degrees. Thus, it only can be bounded up to pi and not 2 pi. So now that we have that, we're going to go ahead and set up the integral. And the integral will be our phi bounds, our theta bounds, and our rho bounds. And we have rho to the 8th, which was our f of x, y, z, and then we have our dv, which is rho squared times sine phi d rho d theta d phi. And the constant 4 from 0 to pi, 0 to 2 pi, 0 to 2. And then we can combine the rho to the 8th power times rho to the 2nd power. We can add the exponents together since they have the same base. And this comes out to be rho to the 10th power. And our sine phi, we can leave it as is. And everything else, we can leave it as is. And now you might be asking yourself, which one is our inner, or why is rho our inner bound and why is phi our outer bound? Well, it honestly doesn't matter. But it's highly recommended that you start with rho first whenever you're given a ball, a perfect sphere, just because it makes the problem a lot easier. So just start with rho first. Notice this function is not multivariable. If it were multivariable, then yes, it would matter, but all these are single variables. So thus our rho bounds are from 0 to 2, our theta bounds are from 0 to 2 pi, and our phi bounds are from 0 to pi. So now let's integrate. And solve. So we have 4 as our constant, we have our phi bounds, our theta bounds, and our inner bounds are going to be our rho bounds. So it's radius 2, so it's 0 to 2, we have rho to the 10th power times sine phi d rho, and then we have d theta and d phi. And the reason I put them closer to the outside than I do towards the inside is so that way you don't integrate with respect to rho or phi. So know that we're integrating with respect to, we're integrating with respect to rho, so do not integrate with respect to phi or theta. And if you know how to do triple or double integrals, you by now should know how to do this. So basically what we're doing is we're going to integrate with respect to rho and then just plug in the bounds. So sine phi, so we can pull out the constant, and when we integrate rho to the 10th power, it's rho to the 11th divided by 11, bounded from 0 to 2. And this in essence is 4 over 11 sine phi times rho to the 11th bounded from 0 to 2. All I did was factor out the 1 over 11. And then from here, it's 4 over 11 sine phi 2 to the 11th power minus 0 to the 11th power. And we know 0 to the 11th power zeroes out, but the 2 to the 11th power does not. And we can change the base of 4 because we know 4 is 2 squared. So we can have a common base. And it's times 2 to the 11th divided by 11 times sine phi. And we know 2 squared times 2 to the 11th is 2 to the 13th over 11 times sine phi. So now let's integrate with respect to theta. So how we're going to integrate with respect to theta. So we know the bounds are from 0 to 2 pi for theta, and we know the inner bound is sine phi d theta. So I'm going to leave a big red note right here. Do not confuse theta with phi. So do not confuse theta with phi. So note what I did right here was I integrated with respect to theta. But note right here, this is sine phi. So this is still a constant. So the constant is not being integrated. We're integrating with respect to theta. So do not confuse phi with theta because it's a common confusion. It happens a lot because they look the same. Because you're probably very familiar with theta, but you're not very familiar with phi. So it tends to happen. So that's why I'm making it clear right here. Do not confuse phi with theta. So sine phi is a constant. And obviously 2 to the 13th over 11 is a constant. So now we're going to plug in the bounds. You get 2 pi minus 0. And we know this one zeroes out. So 2 times 2 pi is 2 to the 14th power divided by 11 times pi, because it's essentially 2 to the 1 power times sine phi. So now let's integrate with respect to phi. So now we're going to integrate with respect to phi. So we're left with 2 to the 14th power divided by 11 times pi. And our phi bounds are from 0 to pi, and we're left with sine phi. So now let's integrate with respect to phi. So we know we have our constant, and when we integrate sine, it's negative cosine phi. And then the bounds are from pi to 0. So 2 to the 14th times pi over 11. And then we're going to plug in the bounds. So negative cosine of pi minus negative cosine of 0. So all I did was this, we're plugging in the bounds now. And we're going to keep the constant on the outside. And we're left with cosine of pi is negative 1. And then we have a minus sign in front of it, so it's minus negative 1. The cosine pi is parentheses. Minus cosine of 0 is positive 1, but we have a minus sign in front of it. So in essence, we got to be very careful when plugging in the pi bound, because cosine of pi is negative 1, so just be very careful. So use a lot of parentheses. So that helps you keep track of your work. And we know that 2 to the 14th times pi over 11. And we know in the blue parentheses, we have 2 minus signs, so it's a plus sign, so it's plus 1. Same thing over there on the right hand side, it's plus 1. Because it's minus negative 1, so it's plus 1. So it's 2. So 2 to the 15th, because it's essentially 2 to the 1 power, and we're multiplying with 2 to the 14th. So 2 to the 15 over 11 times pi. And that's our answer for this spherical coordinate. So the key is to spherical coordinates is to convert them to rho theta phi, which is something you're probably not used to. But for spherical, you have to get used to it. Understand the bounds of integration, which is probably the most trivial part. If it's a perfect ball like this problem was, it's a little bit easier, but that's not always the case. You really have to read the problem, visualize it, draw it out, understand where the bounds are. And now I'm going to proceed on to the next problem. So in this example, we're asked to compute the spherical integral bounded within the region. The region outside the cone of pi over 4 and inside the sphere of rho is equal to 2 cosine phi, cosine phi. So this one's a little bit more trivial. So we're going to start out by trying to draw this out to the best of our ability. And it's kind of hard to draw it on 2D paper, but we're going to try to do it. So x, y, and z axis plus x plus z plus x plus y. Make sure you label which one you're taking positive. So here's our sphere. Our sphere is 2 cosine phi. And our cone is bounded by pi over 4. It's outside the cone. So it's outside the cone, pi over 4. So which means that the cone is bounded essentially from pi over 2 to pi over 4. So this part's kind of trivial, so how did I know this? Well, because it's telling us it's outside pi over 4 and it's within the sphere. But the line of action is happening right at pi over 2. So now let's move on to step 1. So for step 1, quick note, do not confuse theta with phi, two different things, as I previously mentioned, and I will mention it again because it gets people, so don't let it get you. So step 1 is to identify f of x, y, z, and dv. Well, the problem we're given is 1 times dv, so our f of x, y, z is literally just 1, and our dv from our conversions is rho squared times sine phi, d rho, d theta, d phi. So now for step 2, we're going to convert this to spherical coordinates. So we know our f of x, y, z has to go to rho theta phi, and we know 1 dv is equal to 1 times dv is rho squared times sine phi times d rho d phi d theta. And for step 3, we're going to find the bounds of integration. So the bounds of integration are going to be a little bit more trivial than the previous problem just because it's not a perfect sphere, but it's nothing too bad. You just really have to read the region that it's bounded in. That's how you know what's what. So rho is from 0 to 2 cosine phi. On the rho axis, the sphere is within the range of 2 cosine phi, as given in the problem. So the bounds are within the sphere, 2 cosine phi. So that's how we know our phi bound, our rho bounds. So what about theta? Well, theta is just 0 to 2 pi because it was not explicitly stated otherwise what theta is, or what theta, it's basically still a circle. So that's why it's 0 to 2 pi. Phi, it's kind of a little bit more trivial, but we know as we drew it out in the picture, it's from pi over 4 to pi over 2. And we know this because the bounds, the theta angle is from outside the cone of pi over 4 to the z-axis, or the line of action. So basically, this is our phi angle. It's from pi over 4 to pi over 2. Because the z-axis, the positive z-axis is taken from pi over 2. So now that we have our bounds and we have our f of x, y, z, or an f of rho theta phi, we're going to go ahead and set up our integral. So 0 to 2 pi is our theta bound, which is going to be on the outside this time. Pi over 4 to pi over 2 and 0 to 2 cosine phi. Notice how our 2 cosine phi has the most variables, so that's why I decided to include it as the inner limit. And the one with the least variables is 0 to 2 pi, so that's why I have it on the outside. And pi over 2 to pi over 4, since it's something that we had to compute, that's why I decided to keep that inside. But what's less trivial, keep it on the outside. So now our dv is, since our f of x, y, z is just 1, it's rho squared times sine phi d rho d phi d theta. So these are our rho bounds, our phi bounds, and our theta bounds. So now let's integrate. So now let's go ahead and integrate and solve this. So our integral, we're setting up right here. So when we integrate this, we get to cosine phi. So we're integrating, we're going to pull out the sine phi as a constant because we're integrating with respect to rho. So rho squared integrated is rho cubed over 3. Our sine phi is a constant, and this is bounded from 0 to 2 cosine phi. And now we're going to pull out the 3, the 1 over 3, and we're left with rho cubed from 0 to 2 cosine phi. And now let's make a move over here. We know sine phi over 3 is equal to 2 cosine phi cubed minus 0 cubed. And we know that 0 cubed goes to 0, so we're essentially, in essence, we're left with sine phi, and we know 2 cubed is 8, and we know cosine phi cubed is cosine phi cubed. And we're going to pull out the constant 8 over 3 times sine phi times cosine cubed phi. Again, do not confuse theta with phi. So now let's integrate with respect to phi. So we know 0 to 2 pi, and we know the phi bounds are from pi over 4 to pi over 2. And we're left with sine phi cosine cubed phi, d phi, d theta. Do not confuse theta with phi, as I mentioned in the previous problem. It happens, these are both terms of phi, so we have to integrate both of these. In doing so, we're going to have to apply the u substitution because we have a cosine cubed. So in this case, our u is going to be the higher power. So in this case, u is cosine phi du. The derivative of cosine is negative sine. So du is negative sine times d phi. And then we're going to solve for d phi. D phi is equal to du over sine phi. So all I did right there was just apply u substitution because we wanted things in terms of u. So we selected the higher power to be our u variable, and we're going to plug it in, d phi back in, and we're going to plug u and d phi back in, so that way our function is in terms of u. So 8 over 3, bounded from pi over 2 to pi over 4, sine phi u cubed divided by du divided by negative sine phi. So we can cancel out the negatives, we can cancel out the sine phi's, we can pull the negative sign out. So negative 8 over 3, pi over 2, pi over 4, u cubed times du. So now we're going to integrate this now that we have it in terms of u. So our u integrated is 8 over 3, u to the 4th over 4, bounded from pi over 4 to pi over 2. So now, negative 8 times 3 times 4, u to the 4th power, all I did was factor out the 4, bounded from pi over 2 to pi over 4. And we can simplify this because 8 over 4 is 2. So we're going to do that. So negative 2 over 3 times, we're going to plug in the u back in, so it's cosine to the 4th power phi from pi over 4 to pi over 2. And now we're going to simply plug in the bounds. So negative 2 over 3 times cosine to the 4th power pi over 2 minus cosine to the 4th power pi over 4. So in the blue and the teal parentheses, it's pi over 2. In the yellow parentheses, it's pi over 4. So we're going to go ahead and plug in the bounds. So we know negative 2 over 3. We know cosine of pi over 2 is 0 to the 4th power minus cosine of pi over 4. We know pi over 4 is root 2 over 2. So we're going to raise this to the 4th power. And we know this term zeroes out. And in essence, negative 2 over 3 times 0 minus the square root of 2 to the 4th power over 2 to the 4th power. We're going to distribute the 4th power to each term. So we're left with negative 2/3 divided by 0 minus the square root of 2 times to the 4th power is 4, because it's 2 to the 1/2 power times 4, which is 2 squared, which is 4. And 2 to the 4th power is 16. So we're left with negative 2/3 times negative 1 over 4, because 4 over 16 is 1 over 4. The negative signs cancel, and we can simplify this to 2 over 12, which is 1 over 6. So now we can integrate with respect to theta. So now we're going to integrate with respect to theta. So the last problem had a lot of arithmetic. So now we have 1 over 6, 0 to 2 pi. We have d theta, and we're going to integrate with respect to theta. So it's 1 over 6, and then the integral of d theta is just theta, bounded from 0 to 2 pi. And 1 over 6, 2 pi minus 0. This term zeroes out, and we're left with 2 pi over 6, which is equal to pi over 3 when we reduce it. And that's our answer of the volume given between that cone and that sphere mentioned at the beginning of the problem. So this one was trivial because of the bounds of integration. So the key is read the question and understand the bounds of integration. I think the most trivial part was probably the pi over 2, pi over 4 bound for the cone. That's because you have to draw it out, and you have to understand that the cone was given as pi over 4, but the pi over 2, you have to understand that was the line of action where the cone and the sphere were. Other than that, just follow step by step and just practice more spherical coordinates. Thank you for watching. I hope that was helpful. If it was, please feel free to like, share, and subscribe, as I have a lot of content on here, and I will continue to post a lot of content on here to make math and STEM easy. Thank you.